Hello, in this video we're looking at MEI Further Pure 2, the June 2010 paper question 3, which is on matrices. Read through the question first. We're given a characteristic equation and asked to show that lambda equals 2 is an eigenvalue. We're also asked to find the other eigenvalues, so factorising straight away is likely to be the best method. We're then given an eigenvector corresponding to lambda equals 2 and asked to evaluate two calculations and to solve an equation. We're then given a polynomial in M and asked to find constants A, B and C. So that's going to relate back to the characteristic equation, and that's going to be Cayley-Hamilton Theorem. And then finally we're given two eigenvalues and two eigenvectors of a 2 by 2 matrix and asked to find the matrix. So if we're asked to show that lambda equals 2 as an eigenvalue, we could plug 2 into the left hand side and show that it equals 0. But given that we've got to find the other eigenvalues, we're going to have to factorise anyway, so we might just as well start by doing that. So 2 lambda cubed plus lambda squared minus 13 lambda plus 6. If lambda equals 2 is an eigenvalue, then lambda minus 2 must be a factor. So to get lambda cubed, I'm going to need 2 lambda squared. That will give me minus 4 lambda squared, and I want plus lambda squared, so that's plus 5 lambda. That gives me minus 10 lambda, I want minus 13 lambda, so I need another minus 3 lambda, and that gives me the plus 6 that I want. So I can say lambda minus 2 is a factor, so lambda equals 2 satisfies the equation. Which implies that 2 is an eigenvalue. Now I can factorise the remaining quadratic to get 2 lambda minus 1 lambda plus 3. So the other eigenvalues are lambda equals a half and lambda equals 3. Now I'm given an eigenvector corresponding to eigenvalue 2, and therefore m multiplied by that eigenvector must be 2 times the eigenvector, which is 6 minus 6, 2. M squared times a multiple of that eigenvector, so another eigenvector, will be 2 squared times that alternative eigenvector. So that's 4 minus 4, 4/3. I'm then asked to solve this equation. So m x, y, z equals that eigenvector. Well, because I get an eigenvector, x, y, z must also be an eigenvector, so corresponding to the same eigenvalue, so I get this, and therefore that x, y, z is equal to a half 3 minus 3, 1. So x is 3 over 2, y is minus 3 over 2, and z is a half. Now I need to use the Cayley-Hamilton Theorem. So my characteristic equation, which I was given at the beginning of the question, is lambda 2 lambda cubed plus lambda squared minus 13 lambda plus 6 equals 0. Cayley-Hamilton Theorem. Tells me that my matrix satisfies that equation, so 2m cubed plus m squared minus 13m plus 6. Don't forget to put in the identity, we can't mix numbers and matrices. And then rearrange that to get m cubed on its own. So m cubed is dividing everything by 2 minus a half m squared plus 13 over 2m minus 3i. Multiply through by m to the 4 is minus a half m cubed plus 13 over 2 m squared minus 3m. And I don't want any m cubed, so I'm going to replace that m cubed with the line 2 above, which is minus a half m squared plus 13 over 2m minus 3i. That's just substituting for m cubed. Multiplying out, I've got a quarter m squared minus 13 quarters m plus 3 over 2i plus the other two terms. And collecting terms together, I get a quarter plus 13 over 2. 13 over 2 is 26 over 4, so that's 27 over 4 m squared. And 3m is 12 over 4, so minus 12 over 4 minus 13 over 4 is minus 25 over 4m plus 3 over 2i. So A is 27 over 4, B is minus 25 over 4, and C is 3 over 2. That was quite messy as Cayley-Hamilton Theorem questions go, but it's the standard method. Okay, I've got eigenvalues and eigenvectors, so I'm going to create a matrix D, a diagonal matrix D, consisting of the two eigenvalues on the leading diagonal, and a matrix of eigenvectors, making sure I keep them in the same order as my eigenvalues. I'm then going to need the inverse of that matrix of eigenvectors, so that's 1 over 1 minus minus 2, and swap A and D and change the signs of B and C. And then I know that my matrix times the matrix of eigenvectors is the same as the matrix of eigenvectors multiplied by the diagonal matrix of eigenvalues. And that gives me that n is equal to P dP inverse, which I'm now going to calculate. So P is 1, 2, minus 1, 1. D is minus 1, 0, 0, 2. And P inverse is 1/3, 1 minus 2, 1, 1. So I bring the third out the front, multiply my first pair, that's minus 1, minus 2, minus 2, 2. Multiply by 1, minus 2, 1, 1. And that gives me 1/3 of minus 1 and 4 is 3. Minus 1 and minus 2 is minus 3. Minus 2 and minus 4 is 6. And minus 2 and 2 is 0. Giving me the matrix n, 1, minus 2, minus 1, 0. Let's see how the mark scheme works for this question. For part A, there is a single mark for showing that 2 is an eigenvalue either by substituting 2 into the characteristic equation or by factorising. There's then a method mark for doing the correct factorising to get a quadratic and solving that, and 2 accuracy marks for getting each of the correct eigenvalues. For part B, there's a single mark for observing that you need to double the first vector, and two marks for observing that you need to multiply the second one by 4. And for this second one, you allow B1 for 1 sign error. So if you knew to multiply by 4 but made one silly mistake, then you'd get one of the 2 marks. There is, for the second part, a method mark for recognising that the solution is going to be a multiple of the right hand side, and an accuracy mark for getting the correct multiple. For part 3, there is a method mark for using the Cayley-Hamilton Theorem. There's a method mark for multiplying through by m. There's a method mark for substituting for m cubed, and then an accuracy mark for getting down to the correct equation at the bottom with the correct values of a, b and c. Finally, for part B, which is not related to part A, there's a mark for writing down the correct diagonal matrix, a mark for the matrix of eigenvectors. There's a mark with follow-through for getting the inverse of that matrix. There's a mark for this observation here that I need to multiply those 3 matrices together in that order, a method mark for attempting to do so, and an accuracy mark for getting the correct matrix at the end. If you want to find videos of other questions on this unit or on other units, please visit the Further Mathematics Support Programme's website. Goodbye.